Pleasure to introduce Professor Mike Barlow from UCL. And, his title is Detection of a Noble Gas Molecule in the Crab Nebula.
Good afternoon. I'm going to be talking about this afternoon results from Herschel's Spire guarantee time. These came from the Herschel mission, which, as you know, was in operation between June 2009 and the end of April of this year, or 2013 now, of course. This is the team that was using the time to observe the supernova subprogram, and these are the co-authors on the paper that I'm reporting about. So, as part of our guaranteed time observations, we were focusing mainly on imaging observations with Pax and Spire between 70 and 500 microns, looking in particular to characterize the dust component. As you may know, it's believed that supernovae may be a major source of dust in the universe, particularly at high redshifts. And the aim of the program was really to determine just how much dust these supernovae were forming. But a side part of it was to characterize the various interactions between supernova, the circumstellar medium, interstellar dust, and to look for gas diagnostics in kinematics by taking spectroscopy. So just to, before we get on to the Crab Nebula, show results from one of the other supernova remnants, which is Cas A. And here you see 70, 100, and 160 micron composite image. The supernova is the bright, obviously, in 70 and 100 microns. When you get to 160 microns, you're seeing the interstellar medium. And at longer wavelengths, you're completely blocked out, drowned out by the interstellar dust. There's about 6 to 10 magnitudes of extinction towards Cas A. That's why it probably wasn't observed in 1680 when it exploded. Flamsteed may have seen it. Now, here's a Fourier transform spectrometer spectrum that we took of one region in Cas A. We observed 76 different positions in Cas A. This is one of them, and here we're seeing strong emission from carbon monoxide, 3 rotational lines, and carbon-1, 609 and 369 microns. This is coming from material very close to the supernova remnant, but outside it. And it's part of the obscuring material. And in fact, historically, it's important because the first radio molecule detection was of hydroxyl in 1963, which was seen in absorption at 18 centimeters against the non-thermal continuum spectrum of Cas A. Now, turning to the Crab Nebula, this is a composite image made using blue to white is Hubble Space Telescope mission line images joined together, and the red is 70 microns Pax emission. So the red is tracing the cool dust emission in this, and we found about a quarter of a solar mass in this object. Very large, massive dust indeed. But what we're talking about today is the spectroscopy we obtained for it. And this shows the 70 micron image in Pax alone in the background with the positions of the detectors of the Fourier transform spectrometer. It has 2 channels. The short wavelength channel goes from 194 to 313 microns. It overlaps slightly with the long wavelength channel, which goes from 303 to 670. The large white circles have 37 arc seconds. They're the long wavelength channels, determined by the diffraction limit of the telescope. And the green ones are 18 arc second short wavelength aperture sizes, determined again by the diffraction limit of the telescope. So when we took spectral in 7 of the short wavelength detectors and 7 of the long wavelength detectors, we detected very strong unidentified line emission. We had one line only in the spectrum that we could identify, and that's the OH plus hydroxyl ionized iron at 971.8 gigahertz. This is near 300 microns. And it was lucky that we had that line because we could use it as a reference wavelength to work out what the rest frequencies were of the unidentified line. They were the strongest lines in the spectrum. The Crab Nebula has individual clumps and velocity components, as you saw in that earlier image, and they're expanding up to plus or minus 1,500 kilometers a second. So what we had to do was assume that the unidentified lines were coming from the same region as the OH plus lines, work out the radial velocity of the OH plus lines, apply that to the line here in the long wavelength channel, and also to the line in the short wavelength channel. And here again we were lucky because the OH plus line occurs in both of the channels in that small overlap region between them. So that allowed us to then get rest frequencies of 617.554 plus or minus 0.209. We could use 4 of the 7 spectra which had single components. The others had multiple components, and it was harder to do that. For the for the short wavelength channel, we got 1234.786 from 3 spectra with single emission lines or single velocity components. Sorry, if we go back to that, the ratio of those 2 frequencies is 1.995 with a very small uncertainty, which suggests immediately the 2-to-1 to 1-to-0 rotational lines of a simple diatomic molecule. Because we're at high frequencies, it's almost certainly a hydride. And when we then looked at the very voluminous tables of molecular spectra, the one that jumped out was argon H+. J equals 1-to-0, 6.7.525, 2-to-1, 1234.603, which agree within the errors with the measurements. And it's also 36 argon H+. It's not 38 argon H+, and it's not 40 argon H+, because they are shifted sufficiently that we could have measured them. So the frequency is definitely 36 argon H+. These yellow crosses show the long wavelength channel apertures where we detected it, and the red ones show the short wavelength channels. And you can see there's a particular clumping around this southwest part of the nebula, where there's a very bright filament in the nebula. So we think the formation mechanism for the argon H+ is ionized argon in the ionized region interacting with molecular hydrogen in the neutral clumps. And that then gives you argon H+ plus hydrogen and releases 1.49 eV. So it takes a thermic, it's got a fast reaction rate, and it's quite a stable molecule once you have it formed. So although neutral argon is not going to form molecules, argon plus can form molecules. It steals a hydrogen from the molecular hydrogen and you get argon H+. Now, the southern filaments that show the brightest argon H+ are also regions where a paper by Low et al. Published in 2011, where they imaged molecular hydrogen in the 2.12 micron line. They found these white circles were the brightest regions of emission in molecular hydrogen. And there's 7 of them in this same clump that had the strong argon H+ emission. This is a Spitzer image at 24 microns, and this shows positions of the Spitzer spectrometer on the Crab Nebula. And region 1, which Tamin et al. Observed, was found to show extremely strong argon, ionized argon lines. So this is the same region which has the strong molecular hydrogen, and just outside the molecular hydrogen are regions of enhanced argon lines. So here's another image. This is taken in the light of O3 5007 in blue and sulfur 2. Sulfur 2 is a low ionization species, and it's correlating with the molecular hydrogen zones you can see along here. And again, this is the brightest H2 region, molecular hydrogen, I should say, by H2, and also the region of brightest argon H+. Now you can see the continuum emission lines, O3 5007. There's the Crab pulsar, and you can see bow shocks on either side of it. And this is a close-up of that inner region where we're getting this is sulfur 2 coming up strongly, and here again, this region here is the strongest argon H+ and H2. So argon has 3 stable isotopes. They're argon 36, 38, and 40. Now, the argon 40 and 38 2-to-1 lines are displaced by 3.3 gigahertz and 1.75 gigahertz from the argon 36. That's sufficient, even with the low resolving power of the FTS of about 850 at this frequency, for us to put lower limits on the 36 argon to 40 argon ratio of greater than 5, and the 36 argon over 38 argon of greater than 2. Now, for comparison, solar wind has a ratio of 5.5 for 36 over 38. So we're not quite sensitive enough to be able to get down to that level. Now, 36 argon is predicted to be formed by core collapse supernovae. You get 2 oxygen-16 nuclei fusing to give you sulfur 32. Then alpha capture gives you argon 36 and calcium 40. And the Crab Nebula, of course, was a product of such a supernova and was therefore the creation site for argon 36. So the argon 38 isotope is formed by neutron capture onto argon 36 And that ratio is sensitive to the initial heavy element abundances of the star that exploded. So if you can actually measure this ratio, which may be possible in the future, you'll be able to get some handle on the heavy element abundances in the progenitor star. Now, it's worth pointing out that only molecular lines can enable one to distinguish between the different argon isotopes. So this is the first time we've been able to say a particular isotope is in a supernova remnant. The isotopic line splittings of the optical and infrared lines of atoms and ions are much too small to enable one to distinguish between the different isotopes. It was a bit of a puzzle at first because surely argon-40 is a dominant source, a dominant isotope. Well, it is on Earth. After nitrogen and oxygen, argon-40 is the third most abundant species in the atmosphere. 1% of every breath you take is argon-40. It's 24 times more abundant than CO2. And it was first isolated in 1894 by William Ramsay at UCL, who subsequently isolated all the other noble gases in his lab. And in fact, if you go to Astrophysical Quantities, 4th edition, 2000, it gives, in the cosmic abundances table, the atomic weight of argon is 39.948, i.e. argon-40 dominating. Well, that's wrong. It's actually 36 argon is cosmically the most abundant, and that's predicted by nucleosynthesis. 40 argon in the Earth's atmosphere is the product of the decay of potassium-40 in rocks, half-life of 1.25 billion years. So most of the noble gas atoms were lost when the Earth formed. So argon-40 is built up just from potassium-40 decay. The flux ratio of 2 to 1, 1 to 0, between 2 and 2.5, is well below the LTE limit of 30, so we're at lower densities than LTE. And just to skip through this, we didn't have reaction rates or collision rates for electron excitation or molecular hydrogen excitation, which are the most likely excitation mechanisms. So instead, we had to borrow them from helium and silicon hydride, ionized, and H2 plus argon H plus in place of H2 plus argon plus. And in place of electrons and argon H plus, we use electrons and CH plus. Putting those in, if you had H2 as the colliding partner, you'd require densities of 10 to the 6 per cubic centimeter. And if you had electrons, you'd require densities of about 500. Now, the actual molecular hydrogen density has been estimated from the near-infrared lines, about 10 to the 4. So that's well below what you'd require to collisionally excite with H2. So we're therefore plumping for electrons as being the collision partner in the transition zones between the fully neutral gas and the fully ionized gas. So why no detection of neon H+? Because cosmically, neon's 30 times more abundant than argon. And although argon is enhanced in the Crab Nebula, so is neon. Well, 20 neon H+ and 22 neon H+ have got a rotational line, 1 to 0, right in our spectral range, 1039.25 and 1034.79, but they weren't seen. And the reason appears to be that that fast reaction between argon H+ and H2 isn't replicated for neon plus and H2. And that's because the similar ionization potentials of neutral argon and neutral H2, which are like 15.76 and 15.34, leads to a favorable potential crossing curve and a fast reaction rate. Whereas the ionization potential of neon is much higher, and that leads to an unfavorable crossing curve and a low measured rate for the reaction. So that appears to be why we don't see neon H+. Just out of interest, the noble gas molecule that's been sought the longest, over 30 years, is helium H+, because it's believed to have been the first molecule to have formed in the universe after the Big Bang by a slow radiative association reaction between H+ and helium, giving you helium H+ and a photon. However, in this environment, we would look more for ionized helium reacting with molecules. Now here, helium H+ to helium H++ H plus electron is fast. Sorry, I've got that wrong. Yes, that reaction, okay, first of all, helium plus H2 is slow because of the high ionization potential of helium, 24.6 eV. But in ionized nebula, you can get excited helium, neutral helium, in its 2 triplet S state. That will react with molecular hydrogen to give you helium H+ plus a hydrogen atom plus an electron. And that's quite a fast reaction. And the other thing that you have going for you is that the helium to hydrogen ratio is enhanced in the Crab Nebula. It's a factor of 10 larger than cosmic. So together, that might make the Crab Nebula a favorable location in which to find helium H+. And as the last slide, just point out that you don't just get helium H+ in exotic environments like the Crab Nebula. Starting in 2010, Herschel Hi-Fi, the 1 million resolution spectrometer on board Herschel, began to take full spectral scans of a few important satellites, including the Galactic Center, W51, W49. And they found early on in these satellites an unidentified absorption feature, which is between 617 and 618 gigahertz. That's right at the frequency of the J1 to 0, 617.5 argon H+. So it appears to be absorption by argon H+ in ordinary interstellar gas. And you can see in this satellite there's about 20 to 25 individual velocity components along that satellite. Okay, thank you very much.
Questions, comments? Oh, sorry, Ian.
So this quarter of a solar mass of dust in the Crab Nebula, was it all made by the supernova?
Yes. Because this is, as you know, it's only 950 years old. It exploded in 1054, so it has not swept up any interstellar gas at all. In fact, it's in a very low background region. That was one of the reasons it was so easy to measure the dust spectrum, because of no contamination.
And what's the mass? What was the mass of the progenitor star?
It's estimated to have been between 9 and 15 solar masses.
So, okay. So
It was a core collapse supernova.
Okay.